All right, so what we're looking at today is the movement of air and how moisture and energy get added to the atmosphere. So it's a page of notes look like that. All right, so horizontal movement of air is when it goes this way, vertical movement of air is when it goes this way. So let's break it down to its component parts and look at them individually, all right? Now, the one we kind of looked at to some degree already is the vertical movement of air. So things we know about rising air that rises. Rising air is typically warm air because warm air is less dense than cold air is. Rising air is low pressure because remember what air pressure is. Air pressure is the weight of the air on top of you. So if the air above you is rising, it's not pressing down on you as much. Where sinking air is cooler air because it's more dense. And if the air is sinking, it's pressing more on top of you. So sinking air is high pressure. Really haven't addressed moisture with high pressure and low pressure rising and sinking air. Now, normally when you think about like hot, humid air, it feels really heavy and sticky. You'd think that all that water in there would make the air more dense. Actually, it's the reverse of that. Humid air is actually less dense than dry air is. So warm, humid air is the least dense air. That's the stuff that's most likely going to rise. Cold, dry air is the most dense, and that's the stuff that's most likely going to sink. The reason why humid air is less dense than dry air is it has to do, if you look on a periodic table, like air is mostly nitrogen and oxygen. So if you look on a periodic table, see how much atom of nitrogen and how much an atom of oxygen weighs, and then the air that we breathe is N2 and the oxygen we breathe is O2. So if I figure out what the weight of one molecule of nitrogen or one molecule of oxygen is, and then I calculate what the weight of H2O is, which is water, it turns out a molecule of water weighs less than a molecule of either nitrogen or oxygen. So the more water I have in the air, the higher the percentage of water there is in the air, it drags the overall density of that air down because it weighs less. So that's why humid air is less dense than dry air, is because water molecules weigh less than either nitrogen or oxygen molecules. But anyways, so that's also the reason why on hot, humid days is when you're most likely going to get a thunderstorm, because the air has a very low density and is most likely going to shoot up. Okay. So temperature and humidity are some of the things that affect whether air goes up or down. Another thing that can affect whether air goes up or down is the geographic features, such as mountains can alter air movement. All right, so that's what this diagram right here represents. So let's say the wind's chugging along and it hits a mountain. When it hits a mountain, it doesn't just stop, all right? What ends up, because there's other air moving behind it. So that air ends up getting forced over the top of the mountain. Right? Now, whenever air rises, what happens to air as it rises? Well, one thing is air expands when it rises. The higher up you go, the air gets bigger, really spreads out. And the reason for that is the higher up you go, the less air pressure there is. So there's less pressure pushing on the air, so the air will expand. So as it rises, it expands, and as it expands, the air cools down. And as it cools, it eventually reaches that dew point temperature, and you end up with clouds and rain. So this side here is what we call the windward side of the mountain, the side the wind is hitting. Right? Now the air goes over the top of the mountain, and now it's going down this side of the mountain. As the air is going down the side of the mountain, the farther down it goes, the more air pressure there is. That squeezes the air back together. So the air compresses as it sinks, and as the air compresses, it heats up. So it's heating up as it's going down, and it also becomes drier. Because warm air can hold more moisture than cold air. Warm air can hold more moisture than cold air can. Plus it lost a lot of its moisture back here. So this side of the mountain we call the leeward side of the mountain. All right, the dry side. All right. So the reason why the air was going up and down was it was just following the shape of the land, right? And how we have rain on one side and dry on the other, we call that the orographic effect. All right, so that's some of the things that affect the vertical movement of air. All right, now let's focus on the horizontal movement of air. All right, horizontal. Air moves from high pressure to low pressure. All right, well, let's look on diagram here. High pressure is sinking air. So air sinks, hits the ground, and spreads out. Air sinks, hits the ground, and spreads out. Low pressure is rising air. All right, air rises, and then air from the side comes in to take its place. Air from the side comes in to take its place like that. So if I'm a guy who's standing right here, we'll call him Chuck. If Chuck is standing right there, what he's going to notice at the Earth's surface is the air is moving away from the high and towards the low. So air moves from areas of high pressure towards areas of low pressure. Next, close isobars mean high wind speeds. They have a large pressure gradient. All right, so remember what isolines are. Isolines are lines connecting points of equal value. Now, isoline is kind of like the generic term, all right? There are specific types of isolines depending on what you are, what's on your map. So like if I was drawing isolines for temperatures, they'd be called isotherms, all right? If my map has a bunch of different air pressures on it and I connect those, that would be an isobar. So isobars are lines connecting points of equal air pressure. All right. Now, on weather maps, when you draw isobars, what you frequently find is that the isobars make circles around high pressure centers and low pressure centers. Now, with those isobars, what we find is that some places the isobars are going to be spread apart, other places the isobars are closer together. Now, the significance of that is that tells us what the pressure gradient is. Just like when we were doing isolines to show hills and stuff like that, if the lines are close together on a contour map, that means there's a big gradient and the land was very steep. Or if the lines are farther apart, that means the land had a small gradient and the land was pretty flat. Kind of the same idea here. If the lines are close together, that means there's a big pressure gradient. If the lines are farther apart, that means that there's a small pressure gradient. Now, the significance of that is if there's a big pressure gradient, if there's a big change in pressure over a short distance, then you have very strong wind speeds. Right? If they have a small pressure gradient represented by the lines farther apart, that means that the wind speeds are going to be slow. So looking at my little map here, I can tell you right off the bat where the winds are going to be going the fastest. The winds are going to be going the fastest right there because the lines are closest together. All right, so close isobars mean fast wind speeds. All right. Next, as winds are blowing across the Earth's surface, the Earth is rotating. And as a result, those winds get bent. All right, we call that Coriolis effect. We talked about that when we looked at astronomy stuff. So the winds get bent as the Earth rotates. The horizontal winds get bent as the Earth rotates. Now, the Earth is always rotating in the same direction, therefore the winds are going to be bending in the same direction, and that results in the prevailing winds. So the prevailing winds are like the direction the winds normally blow. Now, there's a chart in your reference table that shows you this that we'll get to in a minute. All right. Something that corresponds to the prevailing winds are the ocean currents. The winds blowing over the ocean help stir the ocean currents. So the ocean currents, for the most part, follow the path of the prevailing winds. All right, so we got charts in your reference table that show you this. All right. So this chart here is on page 14 of your reference tables. Planetary wind and moisture belts in the troposphere. So this shows you the direction of the prevailing wind. So, for example, at our latitude, we're at about 42 degrees north latitude. There's 30, there's 60. So 42 would be right about there. So the winds normally come from the southwest. Those are southwest winds. Remember, you always describe the wind by direction it's coming from. If my latitude was like 20 degrees south, you know, there's 0, there's 30 south, 20 south would be right about there. They have southeast planetary winds. So the winds typically blow that way. All right. So this map, this diagram shows you what direction the winds typically blow at what latitudes. Now this diagram here, it shows you what they are on the equinox. So that would be like in March and September. So these can fluctuate some with the season, but this is about what they are in the equinoxes, and it's about what they are. All right, what this chart also shows you is what latitudes are wet and what latitudes are dry. All right, so at the equator is typically a wet latitude. 30 north is typically a dry latitude. So there's lots of rainforests and stuff at the equator. At 30 degrees north, there's lots of deserts. And the reason for that, if I look over here, I can see that at the equator, that's a latitude where the air is normally rising. All right, so if I'm like a little dude standing right there, I'm going to notice the air rising. Rising air, low pressure, rain. If I'm at 30 degrees north, the air is normally sinking at 30 degrees north. Sinking air, high pressure, sunny conditions, so it's usually dry there. So it shows you what latitudes are typically wet and what latitudes are typically dry. And again, that's a result of whether the air is rising or sinking there. What this also shows you is the location of the jet streams. So a jet stream is like a band of really fast moving air. So here's the polar front jet stream, and here's the subtropical jet stream. So it's a really like fast moving band of air that a lot of times separates the colder air from the warmer air. But you know, it shows you their average location in March and September. So these will move based on the season, but that's their average location in March and September. All right, so that's what that map shows you. But for right now, just remember that, okay, so at our latitude, the winds are typically blowing from the southwest. They're typically blowing that way. Remember that. All right, another chart I want to show you. All right, so here is another chart from your reference table, surface ocean currents. So it's a map of the world. But besides that, these arrows here show you the ocean currents, what direction the ocean usually flows. Now, I said remember that at our latitude from the previous chart, the winds typically blow from the southeast. Well, if I look at where we're located, North America, right around there, if I look at the direction that the ocean current's moving right there, it's moving from the southwest to the northeast. So again, the ocean currents generally follow the prevailing winds. Now, it doesn't follow them exactly because when air hits land, air can go right over the top of the land. When water hits land, it has to go around it. So it doesn't follow it exactly, but generally speaking, the ocean currents follow the same direction as the prevailing winds. Now, another thing that's kind of interesting about this map here is besides these currents, and the currents have names on them, like that's the North Pacific Current, this is the South Equatorial Current, the Western Australia Current, and so forth. But besides the fact they have names, this map also tells you whether it's warm water or cold water. And how it does that is that at the bottom of the map, there's a key. at the bottom of the map, there's a key down here where a small solid arrow is warm water and a hollow arrow is cold water. So for example, right here, the Peru current, that's a hollow arrow. So that means the Peru current is cold water coming up from Antarctica. Or the, what is this? I just use the Gulf Stream, the one that goes up the east coast of the United States. Well, that's water, it comes from the equator, so that one's warm water. And I can see that because it has a solid narrow arrow, and the solid narrow arrow down there means warm currents, right? So that's how you use that chart. All right, so again with weather, what people are normally concerned about is what the temperature is outside and whether it's humid or dry outside, so moisture and heat. So how do those things get in the atmosphere? All right, so we're going to look at how, next we're going to look at how moisture and energy get in our atmosphere. So first off with the moisture, there's 3 different ways in which moisture gets added to the atmosphere. First one is one you're probably most familiar with, evaporation. Evaporation is when you go from liquid to a vapor, liquid to a gas. All right? So that's probably the main way that moisture gets added to the atmosphere. Now, there's different things you can do to speed up evaporation. One, so let's say there was a puddle spilled on the floor of this room right here. Things I could do to make that water evaporate faster. One thing is I could add heat. So if I turned up the thermostat and made the air in the room warmer, that would make the water evaporate faster. All right, so warm conditions evaporate faster than cold conditions. That's why your hair dryer blows out warm air instead of cold air, because warm air evaporates faster. And the reason being is because warm air can hold more moisture than cold air can. All right, another thing you can do. All right, again, let's say there was a spill on the floor of this room. What I might do is I might put a fan on that, or I might open up the window so a breeze would go through. Moving air will make water evaporate faster too. And the reason being is if the air is stagnant and not moving, the air right above the puddle might get saturated with moisture, but if you have, and slow the evaporation down. But if I have a new stream of air coming in, a new fresh stream of air, the air is not going to get saturated and it'll evaporate faster. So moving air. So again, that's why hair dryers, they give you warmth and they give you moving air. So they address both those things right there. All right, another thing you might do if you have a puddle on the floor of your room is you might take a mop and you might spread that puddle out. All right, when you use a mop, some of it, the water you're soaking up, but a lot of what you're doing is you're just spreading the water around. And what that does is more of the water to spread out, more of that water is going to be exposed to the air and it's going to evaporate faster. So like if I had a cup of water, like a coffee cup full of water, and I just put it on the counter, I had the same amount of water in a second coffee cup and I dumped it on the ground, the stuff that's poured on the ground would evaporate faster than the stuff's in the cup because the stuff in the ground is going to be spread out more. Right? So more surface area makes it evaporate faster. Next, if the air is dry, it's going to evaporate faster as well. So like in a desert, if you spill some water in a desert, the air is very dry there, it evaporates very quickly. Or in your basement, all right? In your basement, some people have dehumidifiers. So there's a humidifier which adds moisture to the air. A dehumidifier takes moisture out of the air. If I have a dehumidifier, that'll make the air drier and that will allow that air to evaporate things better. All right, so if I can dry the air, that can make evaporation happen quicker as well. So all these things here can make evaporation happen faster. All right. Another way that moisture gets added to the atmosphere is by transpiration. All right. Transpiration is when plants release water vapor into the atmosphere. So plants take up moisture from the roots, they grow through the plant, and then it releases moisture through their leaves. Easy way to remember this one is that trees carry on transpiration. Now, in some areas, this can be a tremendous amount of moisture being added to the atmosphere. The more plants you have, the more transpiration you're going to have. Now, if you just think about like a maple tree, regular maple tree, if I took off all the leaves on that maple tree and then laid them out, that's going to be a tremendous amount of surface area that's releasing air, or excuse me, releasing moisture to the air, much more so than the 20 feet or whatever that the maple tree would take up this way. All the surface area from those leaves can release lots and lots of moisture to the air. Next, sublimation. Sublimation is when ice turns directly into a vapor, or ice turns directly into gas. If you've ever made a tray of ice cubes and you leave it in the freezer for a long time, like say a couple weeks, and you go back and you check in those ice cubes have shrunken quite a bit. The ice cubes did not melt because the temperature in your freezer is below freezing, so it's not going to be a liquid. But what happened, the reason why those ice cubes shrunk is because they sublimated. They turned directly into water vapor. Now this is a much slower process than these guys right here, but it still goes on. Like, let's say you've got a wet t-shirt, and even if it's freezing cold outside, you can put it outside to dry, because what's going to happen is your shirt will freeze, and then as time goes by, it'll sublimate. It'll turn directly into a vapor. Freeze-dried things. The reason why they're freeze-dried is because of sublimation. Right? So this is a very, very slow process. This is a very slow process compared to those guys. All right. So that's the way the moisture gets added to the atmosphere. All right. How does energy get added to the atmosphere? First and foremost, from terrestrial radiation. If you remember what that is when sunlight, insolation, most of insolation does not get absorbed by the air. What happens is that most of it's visible light that travels, hits the ground absorbs it, then the ground starts giving off energy, and that's what terrestrial radiation is. That's where most of the heat in the Earth's atmosphere comes from. Okay. Some other places where it gets heat, condensation of water vapor. You have to add energy to make water evaporate, all right? But if water's going the other way, if it's going from a gas to a liquid, the water loses lots of energy. And something like a hurricane, where you have lots and lots of clouds forming and lots and lots of rain forming, that's a tremendous amount of condensation taking place. That's releasing lots and lots of heat to the atmosphere. Insolation. Now, most of insolation is visible light that passes right through the air. Some insolation is infrared, so there is some energy from the sun that does heat up the air directly. Not as much as what that is, but there is some that's infrared. Wind friction. When the wind blows across the land, it's the same as rubbing your hands together like this. It heats up. Geothermal. The air around something like a volcano, or the air around a hot spring or a geyser, the heat from deep down in the earth can warm up the air in a local area. Chemical reactions. There are some chemical reactions that you have to add energy to them to make happen. Other chemical reactions, when they take place, they release energy. For example, when you mix acid and water together, that's an exothermic reaction that releases heat. Okay? Now, that's not everything. There's other things on there as well. Freezing the water gives off energy too. But that's just some of the main ones right there. All right. So that is horizontal, vertical movement of air and how moisture and energy get added to the atmosphere. Yeah.